Hello, welcome to the second lecture in digital communication systems. In the last lecture, um, I gave you an introduction to communication systems, and we talked about signals and communication systems in general. And today we're going to talk about time continuous signals and systems. And the first part will be about monochromatic signals, as you can see. So this this video is based on the lecture notes chapter 2.1, so you can find additional information there. So first, signals. In the last lecture we talked about signals in general. We had analog and digital signals, and the signals that we consider today are time continuous and value continuous. So they are analog. And we can subdivide signals in a more specific manner. So we have signals which have a periodic pattern. So for example, they are something like this. So they repeat, or there's also periodic signal. And we can have some other signals which have a rather wild shape, so something like this, and there is no repeating pattern inside. So the first categories will be periodic signals, and non-periodic signals. And as you can see, there are also differences between these two signals. We will have a look at this in the second part of today's lecture. But for now, let's just define the terms. You can subdivide periodic signals into monochromatic signals and multi-frequent signals. So monochromatic signals is a signal like this, and multi-frequent signals is a signal like this. Yeah, we will come back to this later. And as you can see in the title of this slide, this part will be about monochromatic signals. So what is a monochromatic signal? In the first slide, I've already drawn a monochromatic signal. Let's redraw it. So let's first draw a proper diagram with the time axis and some kind of value. Let's take in value voltage here as an example, and our monochromatic signal is some kind of sinusoidal function here. So this is in fact a sine or cosine wave, And you see this pattern very often in physics as an oscillation. For example, a spring oscillator. It's a mechanical oscillator. It produces this sinusoidal shape when it starts oscillating. But as we are in digital communication systems, we will consider electronic oscillators. And you all know an electronic oscillator. It's a circuit like this, which consists of an inductance and a capacitor. But how to describe such an oscillation mathematically? We can define a function. Yeah, and this will be our oscillation here. Or we use here oscillation as another term for the monochromatic signal, which is this here. So we have 3 parameters inside here. So the first one is this. This is the amplitude of the signal. Signal has a frequency. And in this case, it is an angular frequency. It's very important that you don't mix it up with other frequency terms. And there is a phase. So how are these parameters connected to the oscillation here in the drawing? The amplitude is the maximum value that the monochromatic signal can take. Here, so the amplitude defines the limits where in the monochromatic signal oscillates. There is a phase. So if we consider here is the time point 0, then the first maximum, and we consider here the first maximum of the monochromatic signal, then the phase defines the shift between the origin, so the time point 0, and the first maximum of the oscillation. So here in this case, the phase is 0. And the frequency, we cannot directly read it from here. It is the frequency defines the periodicity of the signal. But we can read here another parameter, the period of the signal. And the frequency is connected to the period of the signal. The period is just the inverse of the frequency. But as we use here the angular frequency. We have to convert it. So, and here you see why it is important that I've written angular frequency. It's very important that you don't confuse the terms. So this is the angular frequency, and this is an ordinary frequency, or just referred here as frequency. So first attention point, never mix those terms and symbols up. And also don't mix up the units. So the unit of the period is seconds. The unit of the frequency is hertz. And the unit of the angular frequency is 1 by a second, or you can also see notation radians per second, but it's never hertz. Although 1 hertz is technically also 1 by second, but never write this. So you can never confuse the terms angular frequency and ordinary frequency. One point more is that we use here a cosine function, but a sine function will work as well here. So if you remember, sine x is just cosine x minus 90 degree, or p half. So both will work, but we will stick here to cosine function for our considerations. There's another way to consider sinusoidal oscillations or monochromatic signals. So in the mathematical representation we use a cosine function, and now remember where the cosine function does come from. So here's a circle. Oh, that's a bad circle. Let's draw it again. And we place this circle in a Cartesian coordinate system. I name the axis now here real and imaginary axis, so it actually doesn't matter how we call it for now. We will come back to this later. And now let's point an arrow or a pointer here into this circle. The pointer starts at the origin of the coordinate system and ends on the circle here. The arrow has an angel. Let's call it phi. And now what is the cosine? The cosine is the projection of this arrow on the real axis. So this one is the cosine. And remember back to our mathematical representation, there was some kind of, there was the amplitude, and then there was the cosine function. the angular frequency multiplied by the time. Yeah, and then the phase followed, but that is not important for now. By the way, the radius of the circle is here the amplitude, but that's also not important for now. We will just focus here on the cosine function and the most important part of the argument. Here you see that the argument is dependent on time. So there's the time, and as the time advances, also this pointer advances. So in fact it rotates within the circle, and the rotation frequency is the angular frequency. So now you understand why it is called angular frequency. It's the frequency which at which the phase changes, the phase phi. So the argument of the cosine function is that argument phi, what we see here. What we see here, yeah, no. And how do we finally get to our cosine oscillation? So, as I told you, the cosine is the projection of the error on the real axis. So let's consider how the projection changes over time. So let's say that the pointer starts here. This will be our time point 0, or here t equals 0. So let's project it. Project the pointer to here. And as I told you, the initial offset where the pointer starts will be our phase of the signal. So this angle is also the phase. Yeah. And now let's imagine the time advances. The pointer starts rotating into counterclockwise direction. And when the time is, for example, 1, the pointer is at this position. Now let's take the projection. Then we mark here our time point 1. So the pointer will be here. Time point 2. The pointer will be here as well. And finally time point 3. It's here, but maybe it was not drawn correctly. So this is a very bad circle. It should be somewhere here. So now, and the value will be here. So now the time advances. The value decreases. It has a 0 crossing. It passes our value at time point 1. And then there's a turnaround point. The value goes back. has a zero crossing, becomes positive. And now comes back here again, and then it starts all over again. And this point is time point 4. And the time point 4 is exactly where time point 0 is. So here you see that the signal pattern repeats and is periodic. And from this construction method, you can also see the main feature of monochromatic signals. It has only one single oscillation. Yeah, you know, you all just have one cosine function here. And that's enough to construct our monochromatic signal. In electrical engineering, a different notation is used to describe monochromatic signals. It's the phasor representation. What's about this? So, as we have already talked about, there are 3 parameters of our monochromatic signal: the amplitude, the frequency, and the phase. But we will later consider signals which pass through systems. So systems are some mathematical constructs which affect the signal parameters, but it only affects 2 of these 3 parameters, namely the amplitude and the phase. Linear time invariant systems, which we consider here, will never change the frequency. So we now find the representation of our monochromatic signal, which just contains the amplitude and the phase. And this is what we're going to do in our phasor representation. So both parameters, amplitude and phase, are absorbed into a complex number. Let's call it U with a capital letter. And in this lecture, complex numbers are always marked with this underline. So if you see this, it means this is a complex number. And our complex number consists of the amplitude and the phase, which is the argument of the complex number. So this phasor is a complex number in polar notation, with the amplitude here as the absolute value, and the argument is the phase. And now you see why I called the axis here in the Cartesian coordinate systems real axis and imaginary axis, because we will find our phasor here. Phasor is the initial pointer at time point 0. So actually this pointer here drawn in red. This is our phasor, and it has the parameters amplitude, which is the radius of the circle, and our phase, which is the argument. So, and we are going to use this representation very often throughout this lecture.